All right, I'm Hanson Smith, and I'm a postdoc at the University of Connecticut. And today, or whichever day you watch this, I'm going to be talking about non-monogenic division fields of elliptic curves. This is a talk to accompany a recent preprint I put on the archive. And before I dive in, I want to thank the organizers for doing this Junior Mathematicians Research Archive. I think it's a wonderful idea, and I'm really happy to be part of it. So, what's this talk going to look like? First, we're going to start with some motivation and background, trying to frame things in terms of pretty classical stuff. And then I'm going to talk about a couple of results from the preprint. And finally, I'm going to talk about some proof ingredients and ideas for those results. And I'll focus here a lot more on examples. And if you're interested in more technical details, the preprint is the place to go. All right. So let's talk about some cycloatomic fields. So consider the general multiplicative group over Q, which is essentially Q throw away 0. The torsion points of this group are exactly the roots of unity. So the n torsion points are the solutions to the equation x to the n minus 1. And studying these torsion points has been an incredibly fruitful area for a lot of different subjects in mathematics, number theory definitely included. So I want to take these torsion points and throw them into the rational numbers and see what I get. And this is called the nth cycloatomic field, or in analogy with something I'll talk about a little later, the nth GM torsion field. And what does this field look like? Well, it looks like Q adjoins zeta n, where zeta n is a primitive nth root of unity. Okay, so more specifically, what does the nth cycloatomic field look like? Well, that can mean a lot of things. What I mean here is what happens to primes in this number field, and what are the algebraic integers in this number field. So which primes ramify? Well, those are exactly the primes dividing n. So that the ramified primes admit a really nice description. Okay, what about splitting? What's the splitting in inertia? Well, the residue class degree of a prime not dividing n is the least positive integer such that p to the f is congruent to 1 mod n. So excellent description telling us how primes split. And then the ring of integers also admits a really nice description. It's just z adjoined this primitive nth root of unity. So we're really happy. Changing gears a little bit, let's talk about elliptic curves. So if you haven't seen an elliptic curve before, some parts of this talk might be a little rough, but you can think of them as solutions to this equation right here, y squared equals a cubic. And there's also a point at infinity in there. If I want to picture them, they look like donuts. Well, so this was originally a really nice pink frosted sprinkled donut, but I invert the colors on my screen because my eyes get really tired of blue light, and I figured my audience might also appreciate the lack of blue light in this presentation. So now we have an X-ray of a donut. But point being, elliptic curves look like donuts over the complex numbers. And for the purposes of this talk, maybe the best way to think about elliptic curves is they're an abelian group. More specifically, due to Mordell and Vey, if k is a number field, then the points of my elliptic curve over k, well, they have this free part and they have this torsion part. So the integer r, the rank of the free part, and the rank is a rather mysterious quantity, and it's really cool, but we're not going to talk about it anymore today. And then I got this torsion subgroup. And that's the part we're going to talk a little bit more about. Oh yeah, I can denote the intorsion points on my elliptic curve by En, and over the complex numbers, my intorsion looks like Z mod NZ cross Z mod NZ. But of course, over a number field, it might not look like that. It might not be that big. So we're going to study, in analogy with the in-torsion fields of GM, the in-torsion fields of an elliptic curve. And everything's going to be over the rationals in this talk, but of course, a lot of the stuff we'll be talking about admits pretty straightforward generalizations to a number field. So I'm just going to use the rationals here for the sake of exposition. So in-torsion fields of an elliptic curve, take all the in-torsion points of my elliptic curve, throw them into Q, see what I get. So what do I get? Let's compare with our description of the encycloatomic field. Well, the only ramified primes are the primes dividing n and the primes dividing the discriminant. So again, a really nice description of the stuff that ramifies. All right. Ooh, I should have warned y'all before I hit that next. So for splitting it, we need a little bit more notation, but it's still a very nice description. So A sub p is going to be the trace of Frobenius at p. B sub p is the index of the endomorphism ring of my elliptic curve in the maximal order of the imaginary quadratic field that it lives in. And then delta sub end is going to be the discriminant of that endomorphism ring, that order in the maximal order. And I can write down this 2 by 2 matrix. And this matrix is going to tell me a lot about the splitting of primes not dividing the discriminant. And so this little delta is 0 or 1, depending on whether big delta is congruent to 0 or 1. Anyway, the point being is if I know a little bit about the reduction of my elliptic curve modulo p, I know a lot about how p behaves in my in-torsion field. So Duke and Tóth are the people responsible for this. And they show that if n is prime to p, then reducing this matrix sigma p modulo n is going to yield a global representation of the Frobenius class over p in the Galois group of my in-torsion field over Q. So punchline, most relevant for this talk is the order of this matrix mod n is the residue class degree of p in my in-torsion field. So this matrix tells me how p splits in my in-torsion field. And I guess one thing I should have mentioned here, I keep saying residue class degree and splitting being kind of like the same information. Both these number fields are, both these in-torsion fields are Galois. So the in-torsion field of an elliptic curve is Galois, and the encycloatomic field is Galois. Okay, cool. So the motivating question is, can I write the ring of integers of my in-torsion field as nicely as I can write the ring of integers of my encycloatomic field? Can I write it as z adjoined alpha for some alpha? Does it admit a power integral basis? In other words, when is my in-torsion field monogenic? So that's going to be our motivating question. And it's actually a rather difficult question, the problem of when number fields are monogenic. And it's related to a number of other, perhaps more popular questions in algebraic number theory as well. But again, the question's difficult and the relations to other quantities are tenuous and partial. So as we've seen, the GM torsion fields are all monogenic. Super cool. So what about the in-torsion fields of elliptic curves? Well, there isn't a ton of work in this area over Q. I should mention Casanujes and Taylor do have some work mostly looking at CM elliptic curves. It's excellent stuff. But for the purposes of this talk, I will say that the previous work over Q is Gonzalez, Jimenez, and Lozano Robledo show that the in-torsion field coincides with the in-cyclotomic field sometimes. In particular, when n equals 2, 3, 4, and 5, this can happen. So in these cases, because the cyclotomic field is monogenic, I know the in-torsion field is monogenic of this particular elliptic curve. So we know sometimes it's monogenic. So is it always monogenic? And here are some partial results in answering this question. There are a lot of intorsion fields that are not monogenic. And I have main result 1. There's going to be 2 main results, and they're both going to show this lot in different ways. So for the first one, I'm going to take an elliptic curve over Q. And again, this can be done over an arbitrary number field, because Duke and Tóth's result holds over an arbitrary number field. And I'm going to look at its trace of Frobenius at 2. Of course, I can use a lot of small primes here. And so say it has trace of Frobenius A2. And in the next slide, I have a nice table. Well, I think it's nice. You might not. But so for one of the n listed in that table, I'm going to suppose the Galois representation is surjective. So it fills up all of GL2 Z mod NZ. And if this is the case, so we have the trace of Frobenius given in the next slide, the n given in the next slide, Galois representation's surjective, then my n-torsion field is not monogenic. And moreover, 2 is an essential discriminant divisor. So 2 is some fundamental obstruction to monogeneity. Any monogenic order I have, its index in the maximal order is going to be divisible by 2. Okay, so here's the slide I was talking about. On the left-hand column, we have my trace of Frobenius at 2. In the middle, we have Duke and Tóth's matrix. And on the right, we have non-monogenic n. So we can see that when my elliptic curve is supersingular, there are a lot of non-monogenic n. And what this is saying, let's see, what this is saying is that if I have an elliptic curve over Q, its trace of Frobenius is, let's say, -1. And let's suppose that the mod 23 Galois representation is surjective. So the 23rd division field has is as big as possible over Q. In that case, the 23rd division field is not monogenic over Q. And moreover, 2 is an essential discriminant divisor. So 2 is stopping me from being monogenic. And I should explain the blue numbers here are numbers that are no longer, we can't show are necessarily obstructions to monogeneity once we restrict to Serre curves. So with the Serre curve, I have index 2 and GL2 Z hat. So maybe my Galois representation isn't surjective, but it has index 2. And so if I restrict to Serre curves, all the non-blue, white, n are still non-monogenic. So that's due to a result of Jones saying almost all elliptic curves are Serre curves. This says there really are a lot of non-monogenic torsion fields. Okay, cool. So like I said, we can do this for other small primes. Here is the same table for 3. And we notice here I got this B3 quantity, and that's the index of my endomorphism ring over F3 inside the maximal order of my imaginary quadratic field. So with 2, it's always going to be the maximal order, and with 3, when we have trace of Frobenius 0, we can have index 2. Okay, cool. So main result 2. And again, to emphasize, this is another way of saying there are a lot of torsion fields that are not monogenic. So this one's a little simpler to state. Let E be an elliptic curve over Q without CM. Then for infinitely many n, the nth division field is non-monogenic. So if I fix a specific elliptic curve, I'm going to have infinitely many n for which the n division field, the n torsion field, is not monogenic. All right. So let's talk a little bit about what goes into these proofs. So first, we have a classical theorem of Dedekind building really on work of Kummer. I believe Kummer did this for cycloatomic fields, actually. So let F be a monic irreducible polynomial, and let L be Q-adjoined root of F. if I have a prime that doesn't divide the index of z adjoin this root of f in the maximal order of L in the ring of integers. It should be then the factorization of P in the maximal order mirrors the factorization of F modulo P. More specifically, we have this relation. And I just really think this theorem is very, very pretty. It's so cool. This polynomial mod P tells you everything you need to know about P factoring in the ring of integers of L. Okay, so Dedekind actually took this theorem and applied it to monogeneity. So he considered Q adjoin alpha, where alpha is a root of this cubic polynomial here. And we can use sage math. I can use sage math. Dedekind can do it by hand to compute that 2 splits into 3 primes in Q adjoin alpha. So 2's prime factorization is P1, P2, P3. So kind of working backwards here from this theorem, if this number field's monogenic, then I should be able to find, well, I can find a theta so that no prime divides the index of my of z adjoin theta in the maximal order. In particular, 2 won't divide it. So I can find a theta with minimal polynomial f so that f splits into 3 distinct linear factors mod 2 to mirror the factorization of the prime 2 in my number field, right? That's what this theorem of Dedekind and Kummer says. And so we think about this for a second. It's like, okay, what polynomials? I need a polynomial that generates my number field and splits into 3 distinct linear factors mod 2. And of course, we think about it for a second and we realize, well, there are only 2 elements in F2, and so this is impossible. So this number field can't be monogenic. And this was the first example of a non-monogenic number field. Okay, how does this proof work with elliptic curves? And really, I say proof. Main result 1 is more of kind of like an algorithm for finding essential discriminant divisors for various intorsion fields. But we're going to illustrate how it works with an example. So say I have an elliptic curve E with trace of Frobenius 1 at 2. Characteristic polynomial of Frobenius is going to be this polynomial right here. The discriminant of this is -7. That tells me that my z adjoin Frobenius, which is definitely contained in my endomorphism ring of my elliptic curve over F2, is the maximal order, so it must be my endomorphism ring of my elliptic curve over F2. So everything works out really nicely with 2. Right. And so all this information combines to give me this matrix that represents Frobenius. Awesome. So I want to denote the order of this matrix, mod n, like this. And the order of this matrix, to reiterate, is going to be the residue class degree of 2 in my n torsion field. So this matrix right here, reduce mod n, lets me compute the splitting of 2 in my n torsion field when combined with the degree of my n torsion field over Q. So we expect the degree of my n torsion field over Q to be the size of GL2 Z mod NZ pretty often. And so we're going to suppose that's the case. So that tells us if that's the degree of my n torsion field over Q, 2 will split into this many primes. Well, Gauss says the number of irreducible polynomials of degree m is this. So we plug in p equals 2 and m equals the order, and that should tell us, that should give us something to compare with the number of primes 2 splits into. So we're looking for when 2 splits into too many primes to be accommodated by irreducible polynomials of the correct degree. So if the number of irreducible polynomials of the correct degree is less than the number of primes 2 splits into, this GL2 Z mod NZ over the order of that matrix mod N, then 2 must divide the index of any monogenic order in the maximal order. So no monogenic order is going to fill up the whole maximal order. So what we do is we go through in Sage and we look at the order of this matrix modulo different n. And turns out, and this we don't even need Sage, we could compute this, well, we need some free time on our hands perhaps, but we can compute this thing has order 10 mod 11. And so that says that 2 splits into 1,320 primes in the 11 torsion field of this elliptic curve. Well, this elliptic curve, any elliptic curve with trace of Frobenius 1 at 2 and a surjective mod 11 Galois representation. Now, we're looking for irreducible polynomials of degree 10 in F2 adjoint X to match up with the splitting of 2, right? And there are way too few irreducible polynomials of the correct degree to accommodate the splitting of 2. So that tells me that I can't be monogenic. So if E is any elliptic curve over Q with trace of Frobenius 1 at 2, and the size of my 11 torsion field over Q is the size of GL2 Z mod 11Z, then it's not monogenic. And in fact, 2 divides the index of any monogenic order in the maximum order. And so this is kind of how it works, how we figure out, get those tables with non-monogenic n up to 1,000. All right, cool. What about main result 2? So here I'm just going to kind of give a sketch. If I have supersingular reduction at P, and P is not 2 or 3, Duke and Tóth's matrix has a certain shape. It looks like one of these 2 matrices, depending on whether my index in the maximal order is 1 or 2. Okay, cool. I can compute that these matrices have order 2 mod P plus 1. So that's saying that P splits into quite a lot of primes in the P plus first division field, P plus first torsion field. Okay, so I'm splitting a whole lot. It's going to be harder to have the right number of irreducible polynomials modulo of the correct degree. Great. Here in particular of degree 2 in FP adjoint X. So Elkies shows that a non-CM elliptic curve has infinitely many supersingular primes. So cool, we have a lot of primes for which my matrix representing Frobenius looks like one of these 2 matrices. Okay, now the only problem we have to worry about is like maybe for each of these primes, the P plus first division field is really, really small. It's way smaller than GL2's Z mod P plus 1Z. But Serre's open image theorem says that that might happen a few times, but it won't happen forever. So eventually, the image of Galois is always going to be big enough so that we don't have enough irreducible polynomials in FP adjoint X of the correct degree to accommodate the splitting of P. So this shows there are infinitely many primes. So this shows there are infinitely many n for which that are non-monogenic. Specifically, n looks like P plus 1 for super singular primes that are big enough. All right, cool. So natural question is, can it be generalized? Can it be generalized to abelian varieties? And the punchline is yes. Emojis are great. And it's more difficult with abelian varieties, in particular, any sort of supersingularity or partial or drop in the P rank is going to, I don't know how to deal with it. But if we're simple and ordinary and my endomorphism ring looks like this, then we can write down things similar to main result number 1. All right, thank you so much for listening. Feel free to shoot me an email if you have any questions. I believe the preprint I've been talking about is going to be linked in the description of this video. And yeah, thank you for your time.